Hi, everyone. I think we can start. My name is Jose Emilio Muñoz. I'm a software engineer in ARM. And yeah, we'll stay on topic and keep talking about ray tracing. I have been part of the Vulkan samples group in Kronos, where we contributed in ARM several best practice samples and still regularly review them and maintain them and help address new issues and contributions. But I'm here today on behalf of my team, the ecosystem team in ARM, where we do some graphics research and do some techniques evaluation and find some best practices that we can then come and share with you. And in particular today about the Vulkan ray tracing extensions. So I'll take a step back from the previous presentation and do a brief overview of what ray tracing is and what we can do with it. I'll illustrate it with a few more examples like shadows, reflections, and refractions. That give me an opportunity to show you how we implemented some of this and some of the best practices that we found so far. And at the end, I list some resources and some more material that can help you if you haven't done ray tracing before. You'll hear me say Immortalis a few times. Immortalis is the name of our latest Mali GPU. It's our first GPU with hardware accelerated ray tracing. So this means that you now can do ray tracing on mobile devices, and we're very excited to see what games developers achieve with ray tracing now that they can run it on mobile games. So as I said, I'm going to start by introducing ray tracing and how it compares to traditional rasterization. In a typical scenario, you will have something like this, a light, a camera, and a 3D frustum containing the scene that we are rendering. And we will be issuing draw calls object by object. We will transform the vertices and then project all of them onto the 2D screen, check for triangle coverage, and for the pixels that each triangle covers, we will then shade the final color. And we repeat this with every object. And in the case where an object is hidden by some other object, we can check for their depth value in the C buffer, and that way we can resolve those conflicts. For ray tracing, we are taking a completely different approach. In here, we are much more simulating what the light does in the real world as photons of light that travel in all directions. These are our rays. And these rays will bounce around the scene and hit different objects. And as they do so, we can capture some information on the color of those objects until eventually we reach a camera or eyes. And if we do this enough times, then we'll get all the information we need to finish the frame. But as I said, rays go in all directions. So we could have infinitely many rays, and many of these rays will bounce away from the camera. So all the information that they collect will be wasted. So to be more efficient, we do it the other way around. And we trace rays from the camera to the scene. So we can do just one ray per pixel. And in this way, we can get the same final image. I say the same, but I mean here, we need to simplify some things. We'll just take into account a few lights and shade the final color compared to how we do in rasterization. We could take it a bit further and actually get very photorealistic images if we keep tracing rays until eventually we reach the different lights in our scene. And depending on the material, that will give us a much more realistic result. But this means many rays means it's very expensive. So today I'm only going to focus on hybrid applications where we will rasterize our scene using rasterization, but then use ray tracing for very specific effects where they will make the most contribution and achieve a more appealing result. Some of the effects that we have investigated in my team are here. Shadows, reflections, and refractions are the ones I'm going to focus on. As we go down this list, you see that we need more and more rays to achieve these effects, so they become more complex and more expensive. That also means that in some cases, you will have some noise and you will need a denoiser, as we saw. But for today, I'm just going to focus on the ones that don't need denoising. You can get noise-free results with just 1 or 2 rays per pixel. To help me illustrate the different effects, we have a demo that we developed in-house. We had multiple scenes, but this is the Immortalis scene that we have been showing you here. There is a bit of lag in the screen in the room, but I also have the demo running on a mobile phone. So please come and grab me after the talk and I can show you, and you can see the ray tracing up close. And in this scene, what we added was different materials that allowed us to simulate refractions through glass, like the letters here and the cube in the center. We have a light that is attached to the animated object. So this light, as it moves around the scene, is casting the shadows around the room. And as you can see, we also have reflections on the floor and on the walls. And without any optimizations, we saw that this is running quite high FPS, around 40 FPS on the latest Immortalis device that I brought with me. So as I said, we are running this demo using deferred PBR rendering and just doing ray tracing on top of the final image. We're actually basing it on the Vulkan samples framework, the one I mentioned earlier in my talk. This was a quick way to get things prototyped and experiment with these new extensions. First, we need all the G-buffer data. So as we will need to use that for the lighting, and then we can also use it for the ray tracing effects. You don't need to do the ray tracing as a post-processing. We did it this way because we wanted to isolate each effect so we could analyze it and try different optimizations. But in theory, we also tried running them in the same lighting pass, and you can do that with ray query, as I'll explain later. And finally, as it is right now, the demo then combines all these outputs into the final frame. So before I talk about the effects, I want to very briefly introduce the 3 extensions that we have in Vulkan that you need for ray tracing, starting with acceleration structures. So acceleration structures are a way of combining all the geometry data in your scene so that you can very quickly determine if a ray hits something and find out exactly what your ray hit. So this will be typically a tree, but it can be anything. It's implementation defined. The user does have some API options to control the topology. In this case, then, the API makes a distinction between bottom-level structures and top-level structures. A bottom-level acceleration structure is where our geometry actually is. This could be triangles usually, but could also be mathematically defined geometry. And then in here, what we will do to accelerate the traversal and find out what we hit is to subdivide the geometry into bounding volumes. So in this example, you can see that the ray only needs to check the triangles contained in the boxes that the ray hits, and we can discard out of the geometry in that object. We then have to group all these bottom-level structures into a top-level structure. And we do this for a couple of reasons. One is that you can reuse the same bottom-level structure if you have multiple instances of the same object in the scene. And you can do that by associating a transform matrix with that bottom-level structure, and you do this into an instance object. So here you can see how we visualize acceleration structures in our demo. Here we're using the Nsight tool, but we saw on Tuesday that you can also use other tools like the RRA. And what we see is, for example, the spaceship and the geometry in the acceleration structure and the bounding box for that. And as we can see, it's basically another way of representing all the geometry so that we can accelerate and find very quickly what our rays hit. So once we have an acceleration structure, then we need a mechanism to trace the rays and get the information that we need. And as we just saw, we have 2 options in Vulkan, the ray tracing pipeline and the ray queries. The ray tracing pipeline is another kind of pipeline like the graphics or compute, where we have our own well-defined shader stages that I highlight here in orange. We will start with the ray generation shader. Here is where you define your ray to give it a origin and a direction. And then you will kick off a acceleration structure traversal. Here's where the GPU will invoke different shaders depending on what happens. If you have transparent geometry or user-defined geometry, you will need to invoke the any hit or the intersection shaders. But most of the time, you will just arrive at a closest shader or a miss shader. In the miss shader, that means we traversed the whole structure and we didn't hit anything. And the closest hit shader, depending on what we hit, the GPU can invoke a different shader, say you are using different materials, for example. And you will then give that data back to the ray generation shader, which uses it for the rendering. I also added some dotted lines here. That means that in theory, you can also trace new rays from these two shaders, so give you a sort of recursion. But this is not something we recommend since it's quite slow. And for all the effects I'm going to talk about today, you can do them iteratively. You don't need to use recursion. So this gives you a lot of flexibility, but you can imagine it will take a bit more time to set up and define all the shaders. There's another mechanism which we just saw, which is ray queries. Ray queries allow you to do all of this, but in the existing shader stages. So you can do this in compute shaders, fragment shaders most of the time, but even in vertex shaders. And very similarly, what you do is define an array, give it an origin and a direction, and all you do is call a function that is requery proceed. This will kick off the traversal, and then you just have to check for the return value of this function and act accordingly. In terms of what is, if one is better than the other, they're fully compatible. But in our case, we found that requery can make things a bit simpler to implement. And also, since you're running on a fragment shader, that gives you more room for optimizations, like the ones we talked about on Tuesday. We get frame buffer compression, and we can get better use of time memory. So this is the one we prefer. And for all the effects I'm going to talk about now, we could do them with both, but I'm going to focus on requery. Let's start with shadows. A trend that you will see as I talk about the different effects is that with ray tracing, they become very intuitive and easy to understand what we're doing. Whereas in the rasterization world, until now, we have had to implement a lot of workarounds and tricks to make them work. Let's say in the case of shadows, all we need is just one ray per pixel to determine if that pixel is in the light or in the shadow. Because what we do is we trace a ray towards the light. And if this ray hits anything on its way towards the light, we can determine that there is some object in the room that is blocking the light from that pixel. And that is what makes it be in shadow. And as I said, for hard shadows, all you need is one ray per pixel, but we can do even better than that. For example, we can check the angle that this ray makes with the normal at the surface. And if that angle is greater than 90 degrees, you can assume that the light is behind you, and therefore you are in shadow 100%. So in this case, we can completely skip tracing a ray. So we actually need less than one ray per pixel in some cases. I have another video here. We have a debug view to show you how the shadows look in isolation. And yeah, to highlight here the fact that we are using a dynamic light. So the light is attached to the animated spaceship. So it's constantly changing position. With traditional shadow mapping, you will have to regenerate all the shadow maps. And you will likely run into artifacts and other issues to do with the resolution of your shadow map. Whereas with ray tracing, as you can see, we can achieve very noise-free and artifact-free results quite easily, no matter how far away the shadows are. And just for shadows, I'm also going to show how the code looks like. So this is all we need in terms of what we need to do with requery. We have a requery object, which is our ray. We just give it an origin and a direction. When we initialize it, you can see we can also give it some flags that I'll talk about in a bit. Then we just call the function requery proceed. This will start the traversal. And in this case, when the function returns, that means the traversal is complete. And if we hit something, then we are in shadow. For shadows, we can give some hints to the traversal and tell it that to return as soon as we can confidently say that we're going to hit something. To do that, we have the flag terminate on first hit. With this flag, what we're telling the implementation is that if throughout the traversal we can be confident that we're going to hit something, there is no need for us to know exactly what we hit. We can just return, and we'll use that to determine that we're in shadow. And as you can see, we're also filtering any transparent objects by using the requery flags opaque. So for shadows, as I said, it's simple because we don't need to know what we hit. That changes when we come to implement reflections and refractions. Here, we do need to know what we hit because we will be using that color to render our mirrors, for example. And as we saw on Tuesday as well, for this we need bindless resources, and that means using the descriptor indexing extension. We put all the data that we need, all the textures and buffers into arrays, and then we use the information that we get from the acceleration structure traversal to determine what resources to access. So when you hit something in the acceleration structure, you will get some IDs. You will get an instance ID for the bottom level structure that you hit. But then within that, you will also get a geometry ID for the object within that acceleration structure, and even a primitive ID for the exact triangle within that geometry. So we can use this when we're building our acceleration structures to keep track of how many objects are there in each bottom level structure. And then, as well as a transform matrix, we can also associate a custom ID with our instances. And this gives us a unique number for each geometry. We can then use this to index into a lookup table that we bind to the shader. And here we have all the data that we need in order to render the triangle that we intersected. Just in a bit more detail, we have actually two auxiliary lookup tables. We have the mesh ID and the material ID. So from the acceleration structure intersection, we can then narrow down the triangle that we intersected. And we can even get barycentric coordinates. So we then interpolate all the vertex attributes throughout this triangle, and then use the resulting texture coordinates to sample the material that we need. So once you have this in place, that means that no matter where you are in the scene, your array will always have the information that you need to sample anything in the scene. And with that, we have all the ingredients for reflections and refractions. Similar to shadows, here I'm showing a simple diagram for what we need for reflections. We already have an incoming direction towards the mirror. This is obtained from the pixel that we are rendering and the camera position. And then using this simple geometry, we can get the reflection ray direction. And in fact, it's even easier than that. In GLSL and HLSL, you can also just use the reflect built-in function to get your reflection direction. And then use this to define your ray, get the intersection point, and blend that color into the mirror color. Again, this gives us a very intuitive approach to implementing reflections in contrast with what we're using without ray tracing. For instance, you can see here reflections on the curved surface in the pillar. Those are quite hard to achieve without ray tracing. And then the situation here where you have something being reflected that is outside your camera view. For the popular screen space reflections, that's something you cannot do. You will have to just render everything again. And here we can see that we can increment the number of rays to get reflections within reflections and see how the spaceship is reflected on the ceiling back in the floor. But for this, you need an additional ray per pixel. Refractions work in a similar way, but here we actually need two rays. With refractions, what we are trying to simulate is how the light behaves through semi-transparent materials. What's happening is that as we have our light reaching something like glass, is that it will slow down within the object, and then as it comes out on the other side, it will change direction again, and that's what creates this distorted view behind semi-transparent objects. So again, using some physical formulas, we have an index of refraction associated with each material that we can use to exactly determine the angle that the ray will make as it enters and exits the object. And with that and the built-in refract function, we can calculate the new direction of the rays. So with two rays, we can then exit the object and sample the color of anything that behind it. In our demo, you can see here we have the letters of the Immortalis logo and the cube are both refractive. If we just use two rays, then what happens is you will stop your refraction at the second bend, so you won't have refractions behind the cube if you are only focusing on the letters. And as you can see here, that gives us that refractive, that distorted view of the spaceship behind the letter. This is something that maybe you can also approximate without ray tracing, but this is where things get much harder. I saw some implementations where you will have to render the back faces of the object and use the normals there to calculate the new direction. But then you will need to use that to sample some environment map, and it makes it harder to support animated meshes like this. So again, with the concept of rays and ray tracing, you can achieve all this more intuitively and faster. So hopefully that illustrated that requery can be straightforward to implement and does make a difference to the final image. So right now I'm just gonna go through some of the lessons that we learned while we were implementing this, and we're just getting started. We just started doing some more optimization passes and finding out more about what can be done here. To start with, I'll also point you to our free suite of tools called R Mobile Studio. R Mobile Studio contains multiple tools, but the one I'm focusing on here is the offline compiler. Since with rayquery, everything is in your shaders, you can do some static analysis on the shader to find some quick optimization points. For rayquery, we have like a rule of thumb where for every object that you define, for every ray, you shouldn't have more than one initialization call and one traversal call, or at least not more than one traversal call without an initialization before. So here we have an example where we have two proceeds after an initialize. And this is likely to run slowly because we will have a harder time to optimize in the GPU. And the offline compiler will flag that straight away. It does tell you many more things to figure out the bottleneck in your shader, to give you more to get started with optimizations. But in red, I highlight what it tells you about rayquery that is likely to perform slowly. In contrast, if you manage to implement the rayquery so that you only have one proceed for every initialize, then the offline compiler report will show you something like this, that the traversal is likely to be faster. Our Mobile Studio also has a profiler, and it now also supports ray tracing counters. So you can see how many ray misses and other things like that in parallel with everything else that you already get from the GPU. For both ray tracing pipeline and rayquery, as we saw, one of the main bottlenecks is going to be the number of rays. So I showed you a few examples, like for example, with shadows where we could avoid tracing a ray. By having them in a separate render pass, you can also try running them at a slow resolution. So these are several things that you can try to minimize the number of rays. Things like the ray flags to terminate the traversal early are also useful. And for the ray tracing pipeline in particular, there is also some pieces of advice to run faster. We don't recommend doing recursion or doing ray queries within the ray tracing pipeline. And maybe just try using rayquery, as I mentioned earlier. That might give you more options to optimize. And for the effects that I talked about, we could do all of them with both pipeline and rayquery and get the same result. For acceleration structures, some quick advice is to try to play with the options that the API gives you, profile and iterate on that. There is an option to rebuild the acceleration structure in place, which might have some impact in quality, so you need to check and see, but it might be faster. There are also some flags you can use to hint at the GPU if something is going to be rebuilt many times. You can use the prefer fast build option, and also consider the CPU build if the application is GPU bound. As we saw on Tuesday, having overlapping geometries can cause your traversal to be slower. In this illustration, you can see that if you have two bottom level structures that overlap heavily, your ray is going to have to check every geometry object in the scene. Whereas if you do it in such a way that the ray only hits one of those structures, then you can save more time there. As I said, we'll keep investigating, optimizing, and finding more best practices. So we'll keep adding them to this document. Yeah, if you find anything, we're also happy to talk to you and find out what we can do. That being said, we just launched the ARM Developer Program, which is the easiest way to reach us, and also to connect with other developers working on ARM GPUs. Here is where we're going to be posting the best practices and also some blogs and some case studies as we continue working on this. And that's all from me. Thank you. Any questions? Yes, so the question was if there is any more details published about the Immortalis GPU, like in particular hardware details. Yeah, I think the first place to check will be the website that I linked here. We do have some technical details there. I'm not sure to what level of detail you will find, but you're always welcome to message us if there is something there that you need and that is not already there. Thank you.
Okay, so I might make you sweat with this one. If there's something you have to share, I'm going to go out and about slow rate.
Yeah.
And my question is that because you're using the entire super?
Yeah, I'll try to paraphrase. So the question is, what are the technical reasons why we recommend keeping it this way and only using one initialize per, one proceed per initialize? Yeah, I must admit, I'm not super familiar with the details. I know from our compiler team and all the tests that they did, and you probably also can guess why they recommend this. But yeah, my understanding is all to do with giving opportunities to the hardware to parallelize the workloads and do as many races in parallel as possible. And there are just some assumptions that don't hold if you don't follow the best practice, and that cannot guarantee full parallelization. But I don't know the exact details. Any other questions? Okay. Thank you.